student Vyacheslav Balabanov, and we all come from Helsinki. So I first, very shortly, because everybody knows the simplified first strain gradient theory, and I go through very quickly those. Then I think about very practical example truss structures. And then higher order, which is second strain gradient, meaning third displacement gradient. So we use a little bit different terminology. And then lattice structures in that framework. So this is my plan. And this is just a motivation. Motivation for what? To come to Rome to a conference, for at least for me. I don't know about you. Okay, this is from my backyard. yeah. This is well, actually, this could be any of you in Finland. Okay. So, and this is. The first, let's say, metamaterial, it's a lattice, a bar structure. And this is the first one, what I'm using. And then we are going to make beams out of that metamaterial. And we claim that in bending, those behave like a first strain gradient material when we want to homogenize. And how do we homogenize or model? Of course, we can think about 2D homogenized classical continuum, or of course we can model by bars or 2D finite elements very exactly. And this is what we have done, of course. But then from 2D homogenized classical continuum, we want to go to 1D beam. And now the idea is to show that it's not anymore classical beam, but it's in some cases, certain cases, it's a generalized beam. So this is the approach here. And the second example is such that we actually have triple. So here we have triple triangles. So here we have bars which actually jump over one corner. You can see if you look at this guy. And then we even have more. We have next bars which jump across this line here. So we have 3 different bars, or you can say 3 different springs. And my claim is that this works like a second strain gradient or third displacement gradient material. Here you can see the springs. Actually we use bars here, and for the other bars we use springs. Just to make it a bit more clear, but now it's not, you are not seeing it very well. Okay, and then I go very quickly through these basic things because everybody here knows this. So it's Mindlin system that we are using, form 2. And then let's go, but then we use Aalto-Niiranen approach, so only one parameter for simplicity. So this is what we use. And then let's go, all this is known. But now if we want to think about beams, then of course we just take the kinematical assumptions, we plug them in the energy, and see what we get from the principle of virtual work. Okay, this is what we have done. And then we write the weak form or variational formulation of the problem. And now for the because we want to use numerical methods, numerical analysis must be done. And this is why we use Sobolev framework, which is of course very simple in 1D, but in 2D, if we go to plates, it might be a little bit more difficult, and especially when we are now doing shells, then it might be reasonable to use this approach. And you can see that we have here what we have, the higher order gradients in X, and because of the higher order gradients in Z direction, we have this term. which is the stiffening term what always one can see in these beam formulations of generalized continua. Actually one can see those also in modified couple stress theory and microdilatation theory and others. You can see, not the one that Yuri was presenting. And then if we want to study Timoshenko beams, let's say thick beams or somehow Timoshenko-like beams, like sandwiches, what we are going to use, then of course, or even higher order beams, we have also published a paper about so-called ready, or I don't know how to say, but let's say higher order beams. I don't want to use names because somebody gets mad if he's not mentioned. Okay. And this is the Timoshenko problem, and everybody knows that in classical Timoshenko problem we have the so-called locking problem, which is this term. But now we can see that in this case we also have kind of additional locking term here, so just one derivative more. And this is of course from the numerical point of view quite important. And here I shortly explain it. If we scale by EI, then you can see that we have this factor in front of these shear terms, or in front of the shear energy. And of course, because they are of the different order with respect to T with this, which is thickness, then of course in the limit of thin beams we will get locking. This is quite well known in numerical analysis or even in engineering books. And that's why we introduce another weak form where we actually take shear strain as an additional variable. And this is quite well known and used techniques for from recent years. But still one can see that what we get, because here now we don't have any, here locking term here, but we still have one locking term here. So we have EA plus these minus signs here. And then for that we actually need another change of variable, so that finally we have a formulation where we don't have any locking terms, because we, in a way one can say that we have some kind of mass type terms only. Of course we have derivatives, but no locking terms. So this is the formulation that can be safely used for numerical approximations or methods. And then we have, it is actually quite straightforward if you follow basic finite elements or numerical analysis books. One can easily prove that if we are able to use conforming methods, then we will get stable methods. But of course we need this kind of theoretical framework, that we have continuity, ellipticity and uniqueness of the problem in the continuous side. And then for the numerical method we can get error estimates which are so-called quasi-optimal. So let's say the best what you can get. And this one is often called Sia's lemma in numerical analysis. But this is the practical error estimate where we have the convergence rate with respect to h, and then of course the power here is p minus something or p, depending on the problem. And we have done the same stuff for plates, but I'm skipping everything here. And now why we use isogeometric approach, because we want to use conforming methods, which means that in H2 we have to use C1 continuity, in H3 we have to use C2 continuity. So this is kind of the problem, and this is easily done. Well, not easily in a certain sense, but isogeometric analysis gives that easily for certain simple meshes, let's say so. And these are the convergence results. One can easily show that actually this is H3 error here, and it's the energy norm, practically the energy norm. And with different orders, p equal to 3, 4, and 5, you get optimal convergence as what you would expect. And here, actually, I didn't say anything about, but officially, oops, maybe. here you can see that these constants actually depend on G parameter. So it means that our error estimates also depend on G. But we want to show that do they really depend and how much for reasonable range of G parameters, and this is done here. So we use different G values, and one can see that okay, there is a small deviation in the convergence, but not in the rate, but it's just kind of giving a higher constant in front of the estimate. And this is for the Timoshenko beam. You can see that in a very thin Timoshenko beam we have locking. You can see this is the classical convergence estimate or convergence results of the classical formulation. So we really start from the high error level, and then of course we refine and refine and refine. Then of course the error goes down, but it goes unoptimally down. But the other formulations practically give identical results, at least for this case. Of course the other one officially was better than the other one because it was fully locking free, but the other one, there was still one term which was a locking term. So now we can say that okay, we can safely use those numerical schemes. But this is the idea what we have done. So we take a basic truss, and then we duplicate it in two directions, and we repeat. And what it means finally, we can of course, here I just say that of course we can zoom this or scale this such that the overall length is the same. So we kind of get a denser microstructure. This is the idea. And if we use here, thickness is T here of a single strut, and here T over 2. But if we want to use T also here, then when we repeat, then it actually forms a sandwich beam. And these are the two cases, but actually the results are very similar. And now my question is that which one of these beams in bending behaves like a classical continuum? Or which ones and which ones not? So where the microstructure is dense enough in order to kind of be like a classical, okay, you said that in the bottom one. Yeah, that's a good guess. Because in the bottom one it is already like a classical beam, so it can be considered, because when we take a cantilever beam or just a beam and bend it like this, it doesn't matter, you can get the similar results. And then we define relative bending stiffness. So D0 is now the classical bending stiffness, so it's here. Euler-Bernoulli beam would give this one, classical Euler-Bernoulli beam. But you can see that actually the 60 in the bottom one was here, even denser here, but the others are already deviating, so there is a stiffening effect. If you want to model them as a beam, you have to use a generalized beam model. And here the same for the buckling load, P over P0. So it's practically identical. And then if you take the lowest eigenfrequency, there actually only the three coarsest ones don't behave like a classical beam. So, and these ones are quite close to the classical model. And then if you think about dispersion relation, one can show that if we don't take micro inertia into account, which is the green line here, then you don't get exact results. And if you, of course, if you take the classical beam, it's here, you don't get exact results. But if you take micro inertia, you are able to model quite accurately the discrete behavior. And here we have just checked that what is the G parameter. But of course people ask that, is it the dimension, is it the thickness or thickness of the beam or thickness of the struts, or what is it? And now one can see that the thickness of the beam was here 4 millimeters, and thickness of one strut here, or bar here, is 0.5 millimeters, and G parameter is actually 1.57. So it's 1/3 of the height, or 3 times the thickness, but it's not clear that what it is actually. So this is a bit, of course, disappointing. And then we have checked different densities, just making thicker and thicker those struts, just to show that it comes finally to the classical density or classical homogeneous beam, and these are the, and then of course the length scale parameter is 0. So this is the idea of that test. And then we wanted to try that, okay, let's use those in practice. Well, practice, but anyway. We wanted to model by this kind of trusses. These are just single trusses. Of course, one could use multi-trusses here as well, multi-layer trusses. And then we have some joints, and then we model everything by very fine, 2D finite elements. But then we can show that actually our blue lines here, which are the generalized beam, can be used for modeling those struts of the auxetic honeycomb configuration. And here, Timoshenko one, I go very quickly, just to show that there is a difference. If you have a thick beam or short beam, Euler-Bernoulli, green one, it is not close to those dots, which are once again the different discrete multi-trusses. But you need to have Timoshenko. This is for the short one, and this is for the longer one. So we had 2 kinds of Timoshenko beams here. And then we even wanted to play a little bit that, let's say functionally, I would say just graded, not really functionally, because there is now no idea of function. But anyway, we want to model that simple truss or kind of double truss, and this one with a Timoshenko beam. And one can show that classical beams are far too slender, but the generalized one is able to capture the behavior quite nicely. Of course, these are just deflection pictures, so but one could check the stresses or whatever. And here you can use that there is a small kink, of course, in the rotation. Actually, its rotation is still smooth, but you can see that if you use a very fine mesh, you can see that there is a kink in the rotation, as one would expect. And then just a note, I don't go into any details, but we checked a bending with moments here on the top, and then a thermal bending. And that's actually very interesting problem we are now analyzing. We are finalizing a paper about that, and it seems that this gray beam here, which is too stiff, if you don't use gradient of temperature in the entropy. Claudius Duham, there are people who have studied this problem. We are citing to you. Don't worry. but when we use the temperature gradient, then we really are able to capture the behavior correctly. And this was quite surprising, actually. But I don't have anything about that. Okay, then very shortly about the second or the higher strain gradient, we wanted to propose a simple model where we have the first strain gradient ones, then the symmetric second strain gradient ones, and then the cross terms, and then even some kind of linear term there, which is also in the Mindlin's paper, that we kind of played a lot of intuition that which terms should we include. Minimal number, but how many? And then we have made extension tests and other kind of tests and analytical solutions. And this is one of the tests we want to shear. And now we only include 2 different kinds of springs or bars. The third one is neglected because it doesn't matter in this case, in the shear. And one can easily show that actually the effective shear modulus seems to be size dependent. If you just measure classically that what is the shear modulus in this case, this is what you get. And the red line is what our theory of those parameters give us. And how do we get parameters? Actually, by the extension tests and some other tests, we determine one of those, and then the last one with this shear test. So it's matching the curves to the points. And then we still have two inertia parameters, which we also want to match by shearing vibrations. And this is what you can see. Classical elasticity gives you a green line here. So only lowest frequencies can be captured. And then if you include or don't include the inertia parameter, only one, you can get this. But if you include both inertia parameters, then you are getting quite many frequencies quite accurately from the discrete model. Not all the highest ones, of course. Okay, this is just an example. We are not able to model this as a higher order, highest order strain gradient plane problem, but we modeled that for the first strain gradient model. And the problem is in isogeometric analysis that you should have patches like this, and they should be continuous enough from the meshing point of view. And here we were able to get C1, and this is already a task. But we have, then you can, of course, people say that isogeometric analysis is nice because the geometry can be captured accurately, and then we get C1, but the meshing is still a problem. Okay, now I think that I conclude here. It was first and second strain gradient theories for lattices, triangular lattices of different kinds, and then we have to remember that we need some kind of advanced methods in order for the continuities, and then there are boundary conditions, material parameters, how to get homogenized. Okay, we use just simple fitting approaches, and then some references, I think. Okay, thank you.
Thank you very much.
Yeah, thank you.
So we have time for discussion, Simon?
So to get rid of the lock effect, we use some kind of mixed method.
Yeah, well, not really mixed, because there is the number of variables is still the same. So it's practically, I would say, the change of variable.
It's just changing.
Yeah, variable, because you don't have after that rotation, but you have shear. And then in the other one, you don't even have deflection, but you have, or rotation or shear. You have two guys which are kind of some kind of combinations of deflection and rotation.
But this transformation is just possible in the linear case, isn't it?
Well, actually, I haven't thought about that at all. Why? I think why not? I think you can. I don't see any.
I think that the problem is that you can make it in the plane case. Because in plane case, you can is using the axis rotation between the.
Okay. I see.
3D, you can also elimination of torsion. You can.
Okay. Yeah. Okay. If you want to include torsion and yeah, in that, yeah, maybe those cases, you're right. Now this is just yes.
Yuri?
Please, why did you choose the strain gradient theory to describe these lattices? Why didn't you choose some other non-classical theory, for example, micropolar or
yes.
couple stress theory? What is the criteria?
Yeah. Actually, we showed in the first paper there, which is a model comparison paper, and then some numerical results. We showed that actually they all produce more or less the same differential equation. So the results what we propose cover all of them, I would say, and we show it there. And then I would say that the stiffening, if the stiffening effect is the same in the model, then it can be used. So we actually say that it can be, all of them can be used. Modified couple stress, and Lam, and then the microdilatation or something of Young and I don't remember the names anymore, but practically all of those. Not maybe the model that you called microdilatation, but all the existing beam models can be practically used. Yeah.
Question? In fact, I did not understand, what do you call a Timoshenko strain gradient beam?
Yeah, it is just the Timoshenko kinematical assumption, and then you plug it in the strain gradient
Okay, so you
energy.
have freedom of rotation?
Yeah, rotation. Just
It's not
that.
enough to have the strain gradient, is not enough, because the strain gradient is already enriched kinematically.
Ah, okay. No.
Why
Yeah,
you need,
yeah. No, yeah. It is. Yeah. We need. Yeah. We showed that. We showed that it because it's different thing. Of course, even Mindlin writes that Timoshenko, in a way, is or let's say Euler-Bernoulli is a kind of. There is a similar connection between Euler-Bernoulli and Timoshenko than what we have with the micromorphic and the strain gradient. But no, it's because now we speak about kinematical fields, and it's especially in bending, it is different thing. Okay. Yeah, I think that this is the reason that it's about bending.
Okay.
But the results, of course, show also that it's not enough. Yeah.
Okay. No other question, and thank you very much. Yep.